Take an electron and turn it all the way around. One full circle, 360 degrees, the same turn that brings a coin back face up, or sets a spun coffee cup back the way it started, or carries the hour hand of a clock from noon around to noon again. For almost everything in the world, one full turn is a round trip. The thing ends up exactly where it began, with no memory of the journey. Do that same full turn to an electron, and it doesn't come home. Something about it stays flipped, still reversed, still carrying a mark of the trip. To bring an electron truly back to its starting state, it has to go around twice. Two full turns, 720 degrees. One turn leaves it reversed. The second turn undoes the reversal and sets it right. Nothing in ordinary life works like this. A door that needs two swings to shut, a screw that only grips on the second time around the same thread. It sounds like a mistake, or a riddle, or a bad job of turning math into plain words. It's none of those. It's a plain, measured fact about the deepest layer of matter, and the objects that behave this way have a name. They're called spinors. This is the story of those objects, where the strangeness comes from, why it's real, and why it matters more than almost anything. It starts with something that feels completely safe, the ordinary business of turning things around in space. Hidden inside that safe idea, there's a crack, a small piece of two-ness that most people go a whole life without noticing. The crack is exactly the shape of a spinor. From there, the story builds the real mathematics that fills the crack, one piece at a time, and it ends on a single equation written down in 1928 that took this two-turn strangeness seriously. As a direct result, that equation predicted a whole new kind of matter years before anyone had seen a trace of it. And it ends somewhere stranger still. The same two-turn behavior, the thing that makes an electron need to go around twice, turns out to be the reason a table is solid, the reason a hand doesn't pass through a wall, the reason matter takes up room at all. That's a big claim. The story earns it slowly, so it's best to start at the safe end with plain old rotation. Think about turning an object in space, not sliding it, not stretching it, just spinning it around some line while keeping it rigid. A book turned flat on a desk, a globe spun on its stand, a model plane banked and rolled in the air. In every case, the object keeps its shape. Distances between its points stay the same. Angles stay the same. Left stays left and right stays right, so a right hand never turns into a left hand. That last part is what keeps a rotation honest. A mirror flips a hand into its opposite, but a rotation never does. A rotation just moves the thing around while keeping it exactly as it was. Mathematicians gave the collection of all these turns a name. In 3 dimensions, the set of all rotations about a fixed point is called the rotation group, and its short label is SO3. The word group has a precise meaning here. It means a few plain things hold true. Do one rotation, then follow it with another, and the total effect is again some single rotation. Every rotation can be undone by exactly one other rotation, the one that turns the same amount the opposite way. And doing nothing at all, leaving the object right where it sits, counts as a rotation too. The lazy one that changes nothing. Those simple rules, plus the fact that grouping the turns in different bunches doesn't change the outcome, are all it takes to make the rotations a group. There's a clean way to describe any single rotation in 3 dimensions. Pick a line through the center to spin around, the axis, and pick how far to turn, the angle. That's it. That's the whole rotation. This is not obvious, and it has a name, Euler's rotation theorem, after Leonhard Euler, who worked it out in the 1700s. It says that no matter how twisty a turn looks, no matter how many little wobbles seem to make it up, the end result is always a plane spin about one fixed line by one fixed angle. Every rotation, however complicated it sounds, boils down to an axis and an angle. So far, this all feels tame. Here's the first place it stops being tame. The order of two rotations matters. Turn a book a quarter turn one way, then a quarter turn another way, and it lands in one spot. Do those same two quarter turns in the other order, and the book lands somewhere else. The two results really are different. This is easy to check with any boxy object at hand. Lay a phone flat, tip it away, then spin it on the table, and note where the corners point. Start over, spin it on the table first, then tip it away, and the corners point somewhere new. The rotations don't trade places politely. In math language, the rotation group is not commutative, which is a fancy way of saying the order counts. This is already a hint that rotations in space are richer than they look. There's a standard way to write rotations down as numbers, and it helps to know it's there even without doing any arithmetic. Set up 3 arrows at right angles, one along each direction of space, the way the edges of a room meet at a corner. A rotation moves each arrow to a new spot. Line up where all 3 arrows go, and that grid of numbers, 3 across and 3 down, completely describes the turn. These grids are called rotation matrices. They have 2 special features. They keep lengths, so nothing gets stretched, and they keep handedness, so nothing gets mirror flipped. Multiply 2 of these grids together in the way math defines multiplying grids, and the answer is the grid for doing one rotation after the other. The grids capture the group perfectly. Every rotation is one grid. Every grid of this special kind is one rotation. Now for the crack. To find it, stop thinking about any one rotation and start thinking about the whole space of them, not the objects being turned, the turns themselves gathered up into a single shape. Every possible rotation is a point in that shape. The lazy do-nothing turn sits at the center. A small turn sits near the center. A big turn sits far out. The question is what that shape looks like, and the shape has a secret in it. Here's a way to build the shape by hand. Take a solid ball, not a hollow shell, a filled ball, like a scoop of dense clay. Let every rotation be a point somewhere in that clay. The rule for placing a rotation is simple. The direction from the center of the ball to the point tells the axis of the rotation. The distance from the center tells the angle. A point right at the center is no turn at all. A point a little way out is a small turn about the axis pointing toward it. A point near the skin of the ball is nearly a half turn. Let the radius of the ball stand for a half turn, 180 degrees, so the surface of the ball is where the half turns live. Every rotation in 3 dimensions fits somewhere inside this ball of clay. Almost. There's one snag, and the snag is the whole story. A half turn about a line going one way ends up in exactly the same place as a half turn about that same line going the other way. Turn a book 180 degrees clockwise and 180 degrees counterclockwise, and the book lands the same. So those 2 turns are the same rotation, but in the clay ball they sit at opposite points on the surface, on directly facing sides. Since they're really one rotation, those 2 facing surface points have to be treated as a single point. They get glued together. Every pair of directly opposite points on the skin of the ball is pinned into one. The center stays free, the inside stays free, but the whole outer skin gets folded onto itself, each spot joined to the spot across from it. That glued ball is the true shape of the rotation group. It's a real object mathematicians study, and it even has another name, three-dimensional projective space. But the clay ball picture is enough. What matters is the gluing, because the gluing hides a trap. To find the trap, take a walk inside the ball and try to make a loop. Start at the center, the do-nothing turn. Walk straight out in some direction until reaching the surface. That's a growing rotation, about a fixed axis, turning more and more until it hits a half turn at the skin. Keep going, because opposite skin points are glued. Arriving at the surface on one side is the same as instantly being at the point across the ball. So the walk pops over to the far side and keeps coming back toward the center from there. Reach the center again. The walk is now a closed loop. It left the center and it returned to the center, so it's a proper loop, tied off at both ends. In terms of turning, it's a smooth run of rotations that carries an object once fully around, a complete 360-degree turn, and sets the rotations back to rest. Now try to shrink that loop, reel it in, slide it around, deform it any smooth way at all, and try to pull it down to a single point. The way a rubber band on a smooth ball can always be slid up to the top and shrunk to nothing. It can't be done. The loop is stuck. The reason is the gluing. The loop runs from a point on the skin to the point glued across from it, and no matter how the loop is nudged, those two ends stay on opposite sides. Pull one end and the other end swings to stay across from it. The loop can't be freed. It's snagged on the shape of the space itself. That stuck loop is the crack. One full turn, 360 degrees, traces a path that cannot be undone by smooth wiggling. And here comes the surprise that gives the whole subject its flavor. Take that same walk and do it twice. Go from the center out to the surface, pop across, come back to the center, and instead of stopping, keep going. Out to the surface again, pop across again, back to the center again. Now the loop wraps around twice. It's a 720-degree turn, two complete revolutions tied off at the center. A single loop was hopelessly stuck. This double loop is not. It can be slid, step by careful step, all the way down to a single point. The two wraps let each other loose. One of the passes can be slid over to the far side of the ball, where it lines up against the other in a way that lets the whole thing relax and shrink away to nothing. Two turns can be smoothly undone, one turn cannot. That's the crack, stated as cleanly as it can be. In the space of all rotations, a path that spins something around once is caught and cannot be smoothed away, while a path that spins it around twice comes free and shrinks to nothing. There's a real and permanent difference between one turn and two turns, built into the plane geometry of rotating things in space. Mathematicians summarize it by saying the rotation group is connected, meaning any turn can be reached smoothly from any other, but it is not simply connected, meaning some loops in it are stuck. The exact amount of stuckness is small and sharp. Loops come in only two kinds, the ones that can shrink and the ones that can't, and doing a stuck loop twice lands back among the shrinkable ones. That two kinds only fact is called having a fundamental group of order 2, a group with two elements. The whole crack is that little group with two elements. For most of the history of physics, this looked like a curiosity, a fine point about the topology of turning, the kind of thing that lives in a geometry textbook and never bothers anybody. It stopped being a curiosity when the world's smallest pieces of matter turned out to live inside the crack. To see how, the story has to leave pure geometry for a while and go find the electron. The trail starts with a strange experiment done in 1922 by two physicists named Otto Stern and Walter Gerlach. They took silver atoms, heated them into a beam, and shot that beam through a magnet built so that its field was stronger on one side than the other, a lopsided field. The idea was to see how the little atomic magnets inside the silver would get pushed around. If each atom were a tiny magnet pointing every which way, the beam should smear out into a broad band, a continuous fan of atoms nudged by every possible amount. That's what everyone expected, a smear. That's not what happened. The beam split cleanly into two separate spots on the detector, one high, one low, with nothing in between. The silver atoms behaved as though their inner magnets could point only two ways, straight up or straight down along the field, and never anywhere else. No fan, no smear, two spots, and the silver atoms had no orbital motion to speak of, no electron looping around to make a magnet the ordinary way. Whatever was making the two spots was something new, something built into the electron itself, and it came in exactly two settings. It took years to sort out what the two spots meant, and the sorting out was a mess of clever people arguing. The first big move came from Wolfgang Pauli. In 1924, staring at piles of data on how atoms give off light, Pauli decided the electron needed one more label than anyone had given it. On top of everything else that described an electron in an atom, there had to be a new tag with only two possible values. He called it a two-valuedness that could not be described in the old classical way. He was careful, almost stubborn, about not saying what it was. He just said the electron had this extra either-or built in, and the data demanded it. Then a young physicist named Ralph Krennig had an idea about what the two-valuedness might be. Maybe the electron was literally spinning like a tiny top, and the two values were spinning one way or the other. It's the obvious guess. The word spin comes straight from it. Krennig mentioned the idea to Pauli, and Pauli tore it apart. His objection was sharp. If the electron were a little ball of charge spinning fast enough to make the magnetism that showed up in experiments, then the surface of that ball would have to be moving faster than light. And nothing moves faster than light. The spinning ball broke the rules of relativity. Stung by the criticism, Krennig decided not to publish. A few months later, in the fall of 1925, two other young physicists in the Netherlands, George Uhlenbeck and Samuel Goudsmit, landed on the very same idea. The electron spins. They wrote it up and, with a nudge from their mentor, they published. Almost at once, they wished they hadn't. Senior physicists, including Hendrik Lorentz himself, pointed out the same trouble Pauli had. A ball spinning that hard makes no sense. The two young men had put their names on an idea that seemed to be broken on arrival. The nut came loose in 1926, when Llewellyn Thomas cleared up a nagging factor of 2 that had been throwing off the numbers. Once that was fixed, the spinning electron picture matched the fine details of atomic light beautifully. Pauli came around. He accepted that the electron really did carry this inner angular momentum, this spin, but he never budged on the other point. The electron is not a tiny spinning ball. The classical picture of a whirling speck of charge stays wrong, even though the thing it was trying to describe is real. That's the tightrope the whole idea walks. Spin is real. The spinning ball is not. So what is spin if the ball is out? The truth is that spin is a real kind of angular momentum, the physics of turning and twisting that a particle simply has, the way it has mass or charge. It doesn't come from any visible motion. A modern electron is treated as a point with no size at all, and the point can't spin in any picture that means anything. Yet the electron carries angular momentum, a fixed amount of it, as surely as it carries its fixed sliver of electric charge. The amount never changes. Every electron in the universe has the exact same size of spin. What can change is the direction the spin points, and even the direction is caught in that two-spot trap from the silver atom experiment. Here's the trap, said plainly. Pick any direction in space and measure the electron's spin along it. The answer is always one of two values: a little bit one way, or the same little bit the other way, up or down. Never a third of the way, never sideways, never zero, just the two. Turn the measuring gear to a brand new direction and ask again. And again the answer is one of two values along that new direction. The electron never gives a smeared reading. It always picks one of two. This is what physicists mean when they say spin is quantized. It comes in fixed steps, and for an electron there are only two steps to be had. The size of the electron's spin got a number 2. On a natural scale for this sort of thing, the electron's spin is 1/2, half of the basic unit. That's why the electron and its cousins are called spin 1/2 particles, and the name is going to matter enormously before the story is done. Particles come with different spin sizes. Some have spin 0, some spin 1, some spin 2, and those whole number ones are called bosons. The particles with spin that lands on a half, spin 1/2, spin 3/2, and so on, are called fermions. Every particle that makes up ordinary matter, every electron, every quark inside every proton and neutron, is a fermion with spin 1/2. The stuff of the world is spin 1/2 stuff. Now the piece that ties spin straight back to the crack in the rotation group. The state of an electron's spin is described by a small bundle of numbers, and that bundle answers to rotations. Turn the world, and the bundle changes in step, the way a compass needle swings when the room turns. For most familiar things, turning the world all the way around, a full 360 degrees, brings the description right back to where it started. That's the round trip everyone expects. The electron spin bundle does something else. Turn it a full 360 degrees, and the bundle comes back multiplied by -1. Every number in it flips sign. It's the same size, pointing the same way to any measurement. Yet, in its own bookkeeping, it's the negative of what it was. Only after a second full turn, 720 degrees in all, does the -1 cancel against another -1, and the bundle return exactly to its start. That sign flip is not a quirk of one particle. It's the fingerprint of every fermion, and it's the same two-turn behavior that showed up in the clay ball of rotations, now wearing physical clothes. The stuck loop, the one full turn that couldn't be smoothed away, shows up in the electron as a minus sign. The double loop, the two full turns that could be smoothed to nothing, shows up as the minus signs canceling and the state coming home. The math of the crack and the behavior of the electron are the same thing seen from two sides. Pauli, who had refused to picture spin as a spinning ball, ended up being exactly right to refuse. Spin isn't a picture of motion, it's a particle living in the crack. There's a name for the bundle of numbers that behaves this way, that flips sign under one turn and heals under two. That bundle is a spinor. The electron spin is described by a spinor, and the spinor is the mathematical creature carrying the two-turn strangeness. It looks a little like an arrow, an ordinary vector, in that it has a size and it swings when space turns. It parts ways with an arrow in the one place that counts. An arrow doesn't care how it got somewhere. A spinor does. Rotate an arrow around once and it's back. Rotate a spinner around once and it remembers, and the memory is a minus sign. That's the object the whole video is chasing, first met here as the description of a single electron spin. The strangest part of all this is that the two-turn behavior is not hidden away in a lab or locked inside an atom. It can be acted out with a human arm. This is the demonstration Paul Dirac loved to show, and it goes by a few names: the plate trick, the string trick, the belt trick. It even shows up in a Balinese candle dance, where it's called the cup trick. All of them make the same point, with something ordinary held in the hand. Here's the plate version. Rest a small plate flat on an upturned palm, the way a waiter carries a dish. Keep the plate level and keep it facing the same way the whole time. Now turn the hand, plate and all, in a full circle. The plate stays flat, but watch the arm. After one full turn, the arm is wound up, the elbow has swung out and up, and the shoulder is cramped. Everything below the plate is twisted like a wrung towel. In ordinary life, this is where a person stops, because the arm won't go any further without spilling the plate. It feels like a dead end. One turn and the body is knotted. The surprise is what happens by pushing on instead of stopping. Keep turning the plate the same direction, a second full circle, still level, still facing the same way. The first turn carried the hand up and over the shoulder. The second turn carries it back down under the elbow. And as the hand comes around that second time, the arm unwinds. The twist that seemed like a trap slides right out. After two full turns, the arm hangs relaxed again, exactly as it started, and the plate never tipped. Two turns bring the whole system home. One turn leaves it knotted. Anyone with a steady hand can feel the difference in their own shoulder. The belt shows the same thing even more clearly, because a belt keeps a record. Take an ordinary belt with a buckle on one end. Clamp the far end down so it can't move. Hold the buckle out flat and level, with the little metal tongue on it acting as a pointer. Now turn the buckle one full circle while keeping it flat and keeping the pointer aimed the same way. The belt develops a twist along its length. And here's the catch: there's no way to shake that twist out while keeping the buckle flat and aimed the same way. Slide the buckle around any which way, keep it level and point it forward, and the single twist stays. It's locked in. Then turn the buckle a second full circle, the same direction as the first. At first this looks insane, because the belt now seems doubly twisted, worse than before. But it isn't worse. With the belt now carrying two turns, the buckle can be walked around and under the clamped end, always kept flat and aimed forward, and the whole twist comes out. The belt goes smooth. Two turns of twist can be undone by clever looping. One turn cannot. The belt has just acted out the exact fact from the clay ball of rotations, the one turn that's stuck and the two turns that come free. The belt is doing something the plate can't quite show, and it's the heart of why any of this is visible at all. The belt ties the buckle to a fixed anchor, the clamped end. All along its length, the belt keeps a running record of how the buckle got from the anchor to where it is now. That record is the path, the whole history of the turning, not just the final position of the buckle. A plain arrow in space carries no such record. Point an arrow north, spin it around any number of times, and all it knows at the end is that it points north. It forgot the trip. The belt remembers the trip, and because it remembers, it can tell the difference between a path that turned once and a path that turned twice. That memory of the path is exactly what a spinner has, and an ordinary arrow does not. This is why the trick isn't a party stunt or a coincidence. It's a hands-on model of the topology of rotation, the same stuck loop, free double loop business, played out in cloth and skin. The clamped belt is a picture of the rotation group with its history attached. The single twist that won't come out is the stuck loop. The double twist that does come out is the double loop that shrinks to nothing. And the particles that live by this rule, the electrons and quarks whose spin flips sign after one turn and heals after two, are behaving like the belt, not like the arrow. Their spins come back only after two full turns. The arm knows it, the belt knows it, the electron knows it. The rest of the story is about building the mathematics that knows it too, sharply enough to predict things nobody had ever seen. So the rotation group has a gap in it, a bit of two-ness, and the electron falls right into that gap. The natural next question is whether there's a bigger, cleaner shape sitting just above the rotations, a shape with the two-ness ironed out that the rotations are a shadow of. There is. It has a plain job, which is to be the rotation group untangled, and it has a stiff name, the special unitary group in two dimensions, written SU2. Getting to know it is the technical heart of the whole resolution, so it's worth going slow. Start with what its members are. Each one is a tiny square block of numbers, two across and two down, and the numbers are complex numbers. A complex number is just a number with two parts, an ordinary part and a part built from the square root of -1, the famous imaginary unit. Complex numbers are the natural language of anything that turns, because multiplying by them rotates things in a flat plane. So a member of SU2 is four complex numbers laid out in a little square. Two extra rules pin down which little squares are allowed. The first rule, the unitary part, says the block has to preserve lengths when it acts on complex arrows, so it never stretches or shrinks, only turns. The second rule, the special part, fixes a single overall number tied to the block, its determinant, to be exactly 1, which trims away a spare degree of freedom. When the dust settles, every allowed block is built from just two complex numbers, and the squared sizes of those two numbers add up to 1. That last fact is a quiet bombshell. Two complex numbers are really four ordinary numbers, and saying their squared sizes add to 1 is saying those four numbers sit on a sphere. This isn't a plain round sphere in 3 dimensions. It's the big brother 1 dimension up, a sphere living in 4-dimensional space. Mathematicians call it the tree-sphere. So the group SU2, as a shape, is a perfectly smooth sphere in 4 dimensions. Every point on that sphere is one member of the group. It's about as clean and round a shape as exists, and a smooth sphere has no stuck loops. Any loop drawn on a sphere can be slid around and shrunk to a point. Nothing snags. The tree-sphere is simply connected, the exact thing the rotation group failed to be. There's another way to meet the very same group that connects it to an old and beautiful piece of mathematics, the quaternions. Back in the 1800s, a mathematician named William Rowan Hamilton was hunting for a way to multiply points in 3-dimensional space the way complex numbers multiply points in a plane. He couldn't make it work in 3 dimensions. It only worked when he jumped to 4. His quaternions are numbers with 1 ordinary part and 3 separate imaginary parts, usually labeled I, J, and K. They add and multiply by fixed rules, and the one wrinkle is that the order of multiplication matters, just as it did for rotations. The quaternions, whose overall size is exactly 1 form, again a 3-sphere, and those unit quaternions turn out to be the very same group as SU2. The little complex blocks and the unit quaternions are two costumes on one body. This is why quaternions run quietly under so much computer graphics and spacecraft steering. They are the untangled group of rotations, wearing four numbers. Now the payoff, the thing this group was built to do. There's a map that takes each member of SU2 and hands back an ordinary rotation in three-dimensional space. Feed in a unit quaternion, out comes a plane turn of real space. This map respects the group structure, so combining two members of SU2 matches combining the two rotations they point to. But the map is not 1-to-1, it's 2-to-1. For every single rotation in ordinary space, there are exactly two members of SU2 that map to it, and those two are a matched pair. One of them and its exact negative, the same block with every number sign flipped. Both point at the same real-world turn. So the big smooth sphere covers the rotation group twice over. 2 points up on the sphere for every 1 point down among the rotations. This is the double cover, and it's the sharpened, rigorous version of everything the plate and the belt were showing. Walk it around to feel it. Start at a member of SU2 that stands for doing nothing, and let the real-world rotation it points to slowly turn, more and more, all the way through a full 360-degree circle back to doing nothing. Down among the rotations, that's a closed loop, the stuck one. But up on the sphere, tracing along in step, the path has only gone halfway around. It ends at the starting point's negative, the matched partner over on the far side of the sphere, a long way from where it began. One full turn in the world is a half trip around SU2. To close the loop up on the sphere, the real-world rotation has to go around again, a second full turn, 720 degrees, and only then does the path on the sphere return to where it began. The double cover is the reason one turn lands on a minus sign and two turns come home. The minus sign is literally the far point of the sphere. This also says exactly what the rotation group is in terms of the clean one. Take the smooth three-sphere, SU2, and glue each point to its negative, its matched partner. Pinning those pairs together folds the sphere in half and gives back precisely the rotation group with its antipodal gluing the clay ball from before. So the rotations are the double cover sphere with the two-ness folded in, and the sphere is the rotations with the two-ness pulled out and laid flat. The little group of two elements that measured the crack is exactly the pair, a member and its negative, sitting over each rotation. The untangled group has its own honest name in this role, spin 3, the spin group in 3 dimensions, and spin 3 and SU2 are the same group. That word, spin, is not decoration. This is the group that spinors belong to. A spinor is not something the rotation group can act on cleanly, because the rotation group has the crack and can't keep track of the minus sign. The spin group can. It acts on the two-number bundle of an electron spin directly and smoothly, and when a full turn sends a spin group element to its negative, it sends the spinor to its negative right along with it. The double cover is not a piece of trivia. It's the thing that lets spinors exist at all. Everything downstream, the electron's sign flip, the fact that matter is made of two-turn objects, the deep theorem waiting at the end, all of it grows out of this one fact. The rotations have a smooth double, and that double is a sphere in 4 dimensions called SU2. Groups and spheres are lovely, but to actually compute anything about a real electron, physics needs to get its hands on numbers. The tool that made spin computable arrived in 1927, and it came from Pauli again. Having accepted that the electron carries this two-valued spin, He built the smallest possible machine to handle it. 3 little blocks of numbers, each 2 across and 2 down, 1 block for each of the 3 directions of space. They are called the polymatrices, and nearly a century later, they are still the first thing anyone learns when they learn how spin works. Each block is simple enough to say out loud. The block for the up-down direction has a +1 in the top left corner and a -1 in the bottom right, with zeros on the other 2 corners. It reads out the spin along that axis, giving plus for up and minus for down. The block for one of the sideways directions has zeros on the main diagonal and ones on the other 2 corners, so it swaps the 2 slots it acts on. The block for the third direction is similar but built from the imaginary unit, with the square root of -1 sitting in 2 corners with opposite signs, 3 small squares of numbers. Along with the plain do-nothing block, the one with 2 1s down the diagonal, they make a complete little toolkit. These blocks have a handful of neat properties, and each property does a real job. First, apply any one of them twice in a row, and it's the same as doing nothing at all. Each block, multiplied by itself, gives back the do-nothing block. That mirrors the two-valued nature of spin, a switch that returns to start when flipped twice. Second, the numbers down their diagonals add up to 0, a feature with the dry name traceless, which turns out to be exactly what's needed so that these blocks stand for pure spin with no leftover baggage. Third, they equal their own mirror and conjugate, a property called being Hermitian, and that's the technical stamp that lets a block of numbers represent something actually measurable in the lab, a quantity an experiment can read off as a real value. The fourth property is the one that will grow into the deep structure of the whole subject, so it's worth a careful look. The polyblocks do not commute. Multiply the up-down block by a sideways block, and then multiply them in the other order, and the two answers are not equal. In fact, they're negatives of each other. Swap the order, flip the sign. Blocks that behave this way are said to anti-commute. That single feature, that reversing the order of two of these objects flips a sign, is the same anti-commuting behavior that lives at the bottom of Spinors, and it's the thread the next part of the story pulls on. What the blocks are for is measuring the electron's spin. The state of an electron's spin is a bundle of two complex numbers. The spin or met earlier, and each polyblock is the operation of measuring the spin along one axis. Scale the block by half the basic quantum unit, and it becomes the honest spin measurement for that direction. When one of these blocks acts on a spin bundle, the only readings it can ever give back are plus or minus a fixed value, the two settings, up or down. Those two allowed readings are what the silver atoms showed as 2 spots. The whole 2-spot mystery is baked right into these 3 little squares. There's a good reason there are exactly 3 of them, no more and no fewer, plus the do-nothing block. Space has 3 directions, and there's 1 block per direction, but it goes deeper than counting axes. Those 3 blocks plus the do-nothing block form a complete set. Any possible 2 across, 2 down block of complex numbers, anything at all that could act on a 2-number spin bundle, can be built as a blend of just these 4. They are the full alphabet for a 2-state system. That's why a 2-state quantum thing, a single bit of quantum information, a lone electron spin, is described start to finish by the polyblocks. There's nothing else it can do that they don't already cover. The blocks also build the group from the last part. Take the 3 polyblocks, multiply each by the imaginary unit, and what comes out are the basic directions of motion inside SU2, the little nudges that, stacked up over and over, sweep out every member of the spin group. In the language of the trade, the Pauli matrices generate the rotations of the spin group, and the two-turn strangeness falls out of them cleanly. Build up a rotation of a spin one-half particle out of these blocks and carry it through a full 360 degrees, and the machinery returns the spin bundle multiplied by -1. Carry it through a second full turn, all 720 degrees, and the -1 is cancelled and the bundle is truly back. The blocks compute the sign flip that the belt and the sphere only pointed at. There's even a bridge back to the quaternions hiding in here. The three Pauli blocks, each dressed with an imaginary unit, multiply among themselves by the same rules as Hamilton's E, J, and K. Square each to the do-nothing block up to a sign, and get a minus when the order is swapped. The concrete little squares Pauli wrote down to handle the electron are the same quaternions in another outfit, which is the same SU2 in another outfit, which is the untangled rotation group in another outfit. The subject keeps handing back the same object wearing different clothes. With these blocks in hand, Pauli did the thing that mattered. He wrote down a working theory of the electron spin using a two-component spinor, a wave function that carried two numbers instead of one, and let the Pauli blocks push those two numbers around. It was the first real calculating theory of spin, and it matched experiment. It had one limit, and Pauli knew it. His theory did not include relativity, Einstein's rules for fast motion, and for how space and time mix. The electron in an atom moves fast enough for relativity to matter, and stitching relativity into the quantum theory of the electron was the open problem of the late 1920s. Solving it would take a bigger box of these anti-commuting blocks, and a leap nobody had made. Before that leap, though, the anti-commuting trick needs a proper name and a general home, and that home is an algebra discovered decades before anyone had heard of an electron. The home is called a Clifford algebra, after William Kingdon Clifford, an English mathematician who worked it out in the 1870s and died young, at 33, in 1879, long before physicists had any use for what he'd built. What he built is a way to multiply arrows. Ordinary school math never lets a person multiply two arrows and get another thing in the same system. There's the dot product, which turns two arrows into a plain number, and the cross product, which is a special trick of 3 dimensions. Clifford found a single, honest multiplication for arrows that works in any number of dimensions and keeps everything inside one tidy system. The whole thing hangs on one rule, and the rule is almost startlingly simple. An arrow multiplied by itself gives its own length squared, an ordinary number. That's it. Say an arrow has length 1, then that arrow times itself is 1. An arrow of length 2 times itself is 4. A pointed thing squared becomes a plain number equal to its size squared. Everything else about the Clifford algebra follows from insisting on that one rule and then just being consistent. And the thing that follows is the anti-commuting behavior from the Pauli blocks, now revealed as a plain fact about arrows. Take two arrows at right angles to each other and multiply them in the Clifford way, then multiply them in the other order. The two answers are negatives of each other. Swap the order of two perpendicular arrows, and the sign flips. This isn't a new rule bolted on. It's forced by the squaring rule, because squaring the arrow that points between them makes those cross terms cancel, and the only way they cancel is if the two perpendicular arrows anti-commute. So the strange sign flipping that Pauli discovered in his little blocks of numbers was never really about matrices at all. It was the sound arrows make when they're multiplied honestly. The three polyblocks are just the three arrows along the three axes of space, doing exactly what Clifford's rule says arrows must do. This one construction quietly contains a lot of mathematics that people usually meet as separate subjects. Build a Clifford algebra on the smallest space and get the real numbers. Build it on a slightly bigger one and the complex numbers fall out, the imaginary unit appearing as a single arrow that squares to -1. Build it on the next size up and Hamilton's quaternions appear, I and j and k and all. The real numbers, the complex numbers, the quaternions, these hypercomplex systems people invented one at a time over centuries, are all Clifford algebras of small spaces. Clifford found the pattern behind all of them at once. His multiplication carries, in a single package, both the lengths and angles that the dot product measures, and the oriented areas and volumes that the cross product hinted at. It's the natural arithmetic of geometry. Now, why this matters for spinners? Inside a Clifford algebra, one can build the very groups the story has been circling. The spin group is sitting right there, constructed as products of unit-length arrows multiplied together in the Clifford way. Multiply an even number of unit arrows, and out comes a member of the spin group, a rotation with its two-turn memory attached. The double covers, the ones that wrap around the rotation group twice, all come out of Clifford algebras in a uniform way, in 3 dimensions, in 4, in any number of dimensions at all. Whatever the space, it's Clifford algebra hands back the untangled double cover, the home of that dimension's spinners. And here, finally, is where the word spinner gets a hard definition instead of a hand wave. A spinner is a thing the Clifford algebra acts on. Once the algebra is written out as blocks of numbers, which can always be done, a spinner is a column of numbers that those blocks multiply and rearrange. Take a spinner, feed it to the arrows and their products, and it transforms in the special two-turn way, picking up its minus sign under a single full rotation. That's the precise object. No picture, no loose analogy about belts, just a well-defined mathematical creature, a member of the space that a Clifford algebra represents itself on. Everything loose and mysterious about spinners becomes, in this language, exact. That's the gift Clifford's arrow multiplication gives to physics. It turns the two-turn strangeness into arithmetic. There's a lovely way people describe what a spinner is inside this framework. A spinner is something like the square root of a vector. Multiply the right pair of spinners together in the Clifford way, and out comes an ordinary arrow, a plain direction in space. So a spinner is half of a direction, a more basic thing that a direction can be built from, the way the square root of a number is more basic than the number. Great mathematicians have said, quite seriously, that nobody fully understands spinners even now, that their algebra is clear, but their meaning stays slippery, and that they seem to be a kind of square root of geometry itself, as strange in their day as the square root of -1 was when it first appeared. The math works perfectly, the intuition never fully arrives. And that's not a failure of any one person. It seems to be built into what a spinner is. One last piece, because it opens the next door. When physicists write a Clifford algebra for physics, they usually reach for a particular set of anti-commuting blocks called the gamma matrices or Dirac matrices, 4 larger blocks obeying Clifford's rule, each squaring to ±1 and anti-commuting with the others. Those gamma matrices were first written down by Paul Dirac, and he wrote them for one specific reason. He was trying to build a first-order wave equation for the electron that respected relativity, and he needed a set of objects that anti-commuted just so. He was reinventing Clifford's arrows without quite knowing it, and the equation those objects let him write would become one of the most important sentences in the history of science. Before getting to it, the story needs one more group, the one that governs how space and time blend into each other when things move fast. Ordinary rotation turns space around while time sits untouched. Einstein's special relativity from 1905 broke that tidy separation. It showed that, for something moving fast, space and time trade into each other. A moving clock runs slow. A moving ruler shrinks along its motion. Two events that happen at the same moment for one observer happen at different moments for another who's rushing by. Space and time stopped being two separate stages and became one four-dimensional stage, space-time, with a single fixed rule threaded through it. The speed of light is the same for everyone, no matter how they move. Every observer, however fast, measures light going at that one speed. The set of all the ways to shift between observers, while keeping that rule intact, is called the Lorentz group, after the Dutch physicist Hendrik Lorentz, whose equations Einstein built on. It's the symmetry of space-time itself, and it's the deepest symmetry known in physics. Special relativity respects it. The equations of electricity and magnetism respect it. The Dirac equation, still coming, respects it. The whole standard model of particle physics, the best theory of matter there is, respects it. In any small enough patch of the universe where gravity's bending can be ignored, the laws of nature look exactly the same after any Lorentz move. It's as close to a master symmetry as physics has. The Lorentz group has two kinds of moves inside it, and one of them is an old friend. The first kind is plain rotation of space, the same turning that filled the first half of this story. Turn the whole room and nothing physical changes. Those ordinary rotations sit inside the Lorentz group as a familiar piece, the rotation group all over again. The second kind of move is new, and it's called a boost. A boost is what happens when an observer speeds up, sliding into a frame that's moving at a different velocity. And here's the beautiful part. A boost is a kind of rotation too, but a rotation that mixes a direction of space with the direction of time, instead of mixing two directions of space. Ordinary rotation swings the north axis toward the east axis. A boost swings a space axis toward the time axis. It's a turn aimed partly into time. Counting the moves gives the size of the group. There are three independent ways to rotate space, one for each pair of space directions, and three independent ways to boost, one for each direction a thing can start moving. 3 rotations and 3 boosts, 6 moves in all, so the working part of the Lorentz group has 6 dimensions. The rotations among those 6 form a clean self-contained subgroup, the old rotation group untouched. The boosts do not. Do one boost and then another in a different direction, and the result is not a single boost. It comes out as a boost combined with an extra little rotation, a twist that appears from nowhere. That surprise twist has a name, the Thomas rotation, and it's the same relativistic effect that fixed the factor of 2 in the electron's spin back in 1926. The pieces of this story keep quietly connecting to each other. Now for the move that matters most here. Just as the ordinary rotation group had a crack in it and a smooth double cover sitting above, the Lorentz group has the very same feature. It's connected but caught, doubly connected, with loops that need to be traced twice before they come free. And above it sits its own untangled double cover, the spacetime cousin of SU2. This cover has a name of its own, the special linear group in two dimensions over the complex numbers, written SL2C. Its members are, again, little blocks of complex numbers, two across and two down, and again the single overall number tied to each block, its determinant, is fixed to 1. The difference from SU2 is that the length preserving rule is relaxed, because a boost is allowed to stretch and squeeze in the way relativity requires. SL2C is simply connected, smooth, with no stuck loops, and it wraps twice around the restricted Lorentz group, 2 blocks for every spacetime move, a block and its exact negative. That double cover is the reason spinors survive the jump to relativity. SL2C acts on spinors directly, the way SU2 did, and is the thing that lets a spinor be carried smoothly from one moving observer to another, while keeping its two-turn memory intact. Physicists lean on this every time they check that the Dirac equation looks the same to every observer. The spinors of relativity split into two mirror image kinds, a left-handed sort and a right-handed sort, called Weil spinors, and the double cover shuffles them in a fixed way. The details are for specialists. The headline is simple: spacetime, like space, has a smooth double sitting above it, and that double is built to act on spinors. The two-turn strangeness isn't a quirk of slow, everyday rotation. It reaches all the way up into the full symmetry of relativity. So by the late 1920s, all the parts were finally on the table, even if no one had yet fit them together. There was spin, the electron's two-valued inner angular momentum, computed with Pauli's little blocks. There was SU2, the smooth double cover that made the two-turn behavior exact. There was the Clifford algebra, the general home where anti-commuting objects and spinors got hard definitions. And there was the Lorentz group with its own double cover, SL2C, carrying spinors through the fast-moving world of relativity. 4 ingredients, sitting in different corners of physics and mathematics. In 1928, one quiet, exacting man in Cambridge pulled all 4 together into a single line of symbols, and the universe handed back a surprise nobody was ready for. The man was Paul Dirac, and the problem he faced was real and stubborn. Quantum mechanics, as it stood in the mid-1920s, had a famous equation at its core, the Schrödinger equation, and it worked wonderfully for slow things, but it did not respect relativity. It treated time and space differently, in a way Einstein's rules forbid, so it could only be an approximation, good for a slow electron and wrong for a fast one. Everyone knew this was a hole. Schrödinger himself had tried to patch it. He'd written down a relativistic version, now called the Klein-Gordon equation, but it had a flaw. It involved the rate of change in time, a second step in time, and that broke the delicate way quantum mechanics reads off probabilities. It also got the fine details of hydrogen's light wrong. Schrödinger gave up on it and published the slow version that carries his name. Dirac came at it with a stubbornness of his own. At a big physics meeting in 1927, he grew annoyed that so many brilliant people were willing to swallow the flawed relativistic equation and abandon the basic principles of quantum mechanics to do it. He would not abandon them. He went back to Cambridge, and within about 2 months, he cracked it. He published on the 2nd of January, 1928, and physics was never the same. His method was guided by 2 demands he refused to bend on. First, the equation had to look the same to every observer, fast or slow, so it had to respect the Lorentz symmetry of spacetime. Second, it had to involve only a single step in time, a first rate of change and no more, so that the quantum reading of probabilities stayed intact. Those 2 demands seemed to be at war. Relativity ties energy to momentum through a square root. The energy of a particle is the square root of its momentum squared plus its mass squared in the right units. Square roots are exactly the kind of thing that make an equation clumsy and full of higher steps. To get a clean first step in time, Dirac had to somehow take the square root of that whole expression and have it come out simple. His idea was the turn of genius. He asked whether there were special quantities that could stand in front of the momentum and the mass so that the whole square root flattened into a plain sum, a first-order expression with no root left. Squaring such a sum brings out all sorts of cross terms, and for them to cancel and leave the correct relativistic relation, the special quantities had to obey one strict rule, each squared to a fixed value, and any two of them multiplied in opposite orders gave opposite signs. They had to anticommute. That's the Clifford rule again, the arrow multiplication from before, the same sign flipping Polly had found in his little blocks. Dirac had walked straight into a Clifford algebra by chasing a square root. And here's the thing those anti-commuting quantities cannot be. They cannot be ordinary numbers. No plain numbers anti-commute, because for plain numbers, the order of multiplication never matters. The quantities had to be blocks of numbers, matrices, and the smallest blocks that would do the job were 4 across and 4 down, 4 larger cousins of the Pauli blocks, anti-commuting, each squaring to plus or minus the do-nothing block. These are the gamma matrices, the Dirac matrices, and they are the concrete Clifford algebra of spacetime. Now trace the consequence, because it's the whole point. If the operations in the equation are 4 by 4 blocks, then the thing they act on, the wave function of the electron, cannot be a single number the way Schrödinger's was. It has to be a bundle of 4 complex numbers stacked in a column, so the blocks have something 4 tall to push around. The electron's wave function had to become a 4-part object. That 4-part object is a spinor, the Dirac spinor, the abstract creature from the first half of the story, the thing that flips sign under one turn and heals under two, turned out to be the only shape the electron's description could take once relativity and quantum mechanics were both honored. Dirac didn't reach for spinors on purpose. The demands of the problem forced them on him. To describe an electron correctly, the universe insists on a spinor. The first payoffs were staggering, and they arrived fast. Spin came out of the equation on its own. Dirac had not put spin in by hand. He'd asked only for relativity and quantum mechanics in one consistent package, and the electron spin 1/2, the two-valued inner angular momentum that Pauli had bolted on by hand and Uhlenbeck and Goudsmit had guessed at, fell out automatically as a built-in feature. Spin was revealed as a consequence of combining relativity with the quantum world. 2 of the 4 numbers in the Dirac spinor behaved, for a slow electron, exactly like Pauli's spin up and spin down. The equation explained why the electron has spin at all. On top of that, it reproduced the fine structure of hydrogen's light, the delicate splitting of spectral lines, exactly and from first principles, something no earlier theory had done cleanly. Within the year, other physicists confirmed it matched the measurements to the letter. It's hard to overstate how this landed. For the first time, quantum mechanics and special relativity sat together in a single equation with no cheating, and that equation described the most important particle in ordinary matter, and it got the numbers right, and it handed back the electron's spin as a free gift. Physicists have ranked it with the work of Newton and Maxwell and Einstein. Some have called it the real seed of modern physics. It became a cornerstone of the Standard Model, and when Dirac died, the equation was carved into a stone marker set in the floor of Westminster Abbey, near the graves of the greatest names in British science, unveiled in 1995, a line of mathematics cut in green slate honoring a man who found the shape of the electron. But the equation had a loose thread, and Dirac, careful as he was, could not make it go away. Along with the sensible solutions, the ones describing an ordinary electron with ordinary positive energy, the equation coughed up a second family of solutions with negative energy. Energy less than nothing. On its face, that's nonsense. A particle can't have less energy than empty space. Dirac's first instinct was to wave the bad solutions off as unphysical junk to be ignored, but quantum mechanics wouldn't let him. The math tied the good solutions and the bad ones together so tightly that an ordinary electron could, in principle, tumble down into the negative energy states and vanish from the visible world. The solutions could not simply be crossed out. They meant something. Working out what they meant would take Dirac to one of the boldest predictions ever made in physics. And it's a story about a man deciding to trust his own equation more than his common sense. It helps to know who Dirac was, because the prediction he made fit his character exactly. He was born in Bristol, England, on the 8th of August, 1902. His father was an immigrant from Switzerland, of French descent, a French teacher, strict to the point of harshness. He made his children speak to him only in French at the dinner table so they'd learn it. When young Paul found he couldn't say what he meant in French, he simply said nothing. He grew up quiet, and he stayed quiet. He trained first as an electrical engineer at Bristol, couldn't find engineering work in the slump after the war, studied mathematics instead, and finally landed at Cambridge, where in 1926 he finished the first doctoral thesis on quantum mechanics ever written anywhere. The stories about his silence are famous, and they aren't cruel, just precise, like him. His colleagues at Cambridge jokingly proposed a unit of talking, 1 word per hour, and named it the Dirac. When someone struggling to finish a written sentence asked him for help, Dirac reportedly said he'd been taught never to begin a sentence until he knew how it would end. He had little patience for poetry, remarking that science tries to make hard things plain, while poetry tries to make plain things sound hard, and that the two aims didn't sit together. Niels Bohr, who ran the Great Physics Institute in Copenhagen and knew everyone worth knowing, called Dirac the strangest man who'd ever come to visit. Bohr also called him a complete logical genius. Underneath the silence was one guiding belief that runs through everything Dirac did. He thought the laws of nature should be beautiful as mathematics, and that beauty was a real clue to truth. Faced with a choice of directions, he'd take the one with the cleaner, lovelier math, and he trusted that nature would agree. He said as much for the rest of his life, that a physical law of great mathematical beauty was more likely to be right than an ugly one that happened to fit the data. Hold that belief in mind, because it's the key to what he did next. A man who trusts the beauty of an equation over his own gut is exactly the kind of man who will believe an equation when it tells him something absurd. Back to the loose thread, the negative energy solutions. At first, Dirac did the ordinary thing and tried to ignore them. That stopped working in 1929, when Oscar Klein showed that in the presence of forces, the good solutions and the bad solutions inevitably mix. An electron sitting happily at positive energy could slide down into the forbidden negative energy states. There was no clean way to forbid it. Dirac's first response was to suspect his own equation of being flawed, a rough first draft of some better theory to come. Then he found a way to make peace with the negative energies that was so strange it's almost hard to believe a careful man proposed it. He proposed that empty space is not empty. He suggested that every one of the negative energy states is already filled, everywhere, all the time. The vacuum on this picture is a bottomless sea of negative energy electrons packed into every available slot, an infinite ocean we never notice because it's uniform and always there. This came to be called the Dirac Sea. And the reason a positive energy electron can't fall down into the negative states is that the slots are already taken. This is where Pauli's exclusion principle walks on stage, the rule that two electrons can't crowd into the same state. With every negative energy slot occupied, the exclusion principle bars any more electrons from joining. The full sea holds the line. That's what keeps ordinary electrons from tumbling into oblivion. Then Dirac took the idea one step further, and the step was the masterstroke. If the sea is normally full, what happens if one negative energy electron is missing, leaving a gap, a hole in the sea? The surrounding sea has a net charge, and the missing negative charge in it would behave from the outside like a present positive charge. A hole would look and act like a particle with positive electric charge. So Dirac's equation seemed to predict positive particles made of absences. His first guess for what they were was the proton, the only positively charged particle anyone knew of at the time. It was a natural guess, and it was wrong. Robert Oppenheimer pointed out that if the holes were protons, ordinary atoms would destroy themselves almost instantly as their electrons dove into the holes, and Hermann Weyl showed, from the symmetry of the math, that a hole had to have exactly the same mass as an electron. A proton is nearly 2,000 times heavier. The hole could not be a proton. Faced with that, most people would have concluded the whole sea idea was broken. Dirac concluded something braver. If the whole can't be any known particle, then it must be an unknown one. In 1931, he published a paper predicting a genuinely new particle, one nobody had ever seen, which he called an anti-electron. It would have the same mass as the electron and the opposite, positive charge, and when it met an ordinary electron, the two would annihilate each other and disappear in a flash of light. He went even further and suggested that this might be general, that every kind of particle could have an oppositely charged twin. That idea is what we now call antimatter, and Dirac reasoned his way to it from nothing but the structure of his own equation and the refusal to look away from what it was telling him. Sit with how odd that is. There was no experiment crying out for a new particle. There was no gap in the data. There was only an equation built to marry relativity and the quantum world that kept producing solutions its author found embarrassing, and a man who trusted the equation's beauty enough to say those solutions must describe something real. He predicted a whole new form of matter because the mathematics left him no honest way out. It was the first time in the history of physics that a fundamental particle was called into existence by pure mathematical necessity, named and described in detail, before anyone had the faintest experimental sign of it. All that remained was for the universe to be checked, to see whether it had actually bothered to build the thing Dirac's Spinors demanded. The check came from the sky, from a young experimenter named Carl Anderson, working at Caltech in California. Anderson wasn't hunting for Dirac's particle. He was studying cosmic rays, the shower of high-energy particles that rains down on the Earth from space, and he was watching them with a cloud chamber. A cloud chamber is a simple, gorgeous instrument. It's a sealed box of vapor so ready to condense that any charged particle streaking through leaves a thin trail of droplets behind it, like the white line a jet scratches across the sky. Anderson wrapped his chamber in a strong magnet, which bends the trails. A positive particle curves one way, a negative particle curves the other, and how tightly it curves reveals its mass and its charge. On the 2nd of August, 1932, Anderson photographed a track that made no sense at first. It curved the wrong way to be an electron, but it was far too gently curved, far too light to be a proton, the only positive particle known. He'd put a lead plate across the middle of the chamber, so a particle passing through would lose speed and curve more tightly on the far side, which told him which way it was traveling. Reading it carefully, the answer was undeniable. Here was a particle with the mass of an electron and a positive charge, a positive electron, exactly the anti-electron Dirac's equation had called for the year before. The particle got its name almost by accident. Anderson didn't coin the word. When he sent his discovery to a journal, an editor suggested calling it a positron, and Anderson let it stand. The positron was the first piece of antimatter ever seen, and for finding it, Anderson won the Nobel Prize in Physics in 1936 at a strikingly young age. Here's the detail that makes the whole thing land harder. By the usual telling, Anderson found the positron on his own from the cosmic ray data, without leaning on Dirac's theory at all. He was reading tracks in a cloud chamber, not testing a prediction. If that account is right, and it's how the story is most often told, then the confirmation is about as strong as confirmation gets. Two completely separate roads, one running through pure mathematics in Cambridge and the other through photographs of cosmic rays in California, arrived at the very same particle. The theorist reasoned it into existence from the structure of an equation. The experimenter stumbled onto it in the sky, and they matched. Same mass, opposite charge, just as the math had said. The positron had come tantalizingly close to being found before, which only makes the near misses sting. As far back as the early 1920s, a physicist named Dmitry Skobeltsyn had seen tracks that curved the wrong way and hadn't known what to make of them. A graduate student at Caltech named Chung Yao Chao, a classmate of Anderson's, had noticed strange results pointing the same direction a few years earlier, though they were inconclusive and went unpursued. Anderson later acknowledged that Chao's work had helped inspire his own. In Paris, Irene and Frédéric Joliot-Curie had positron tracks sitting in their old photographs and had dismissed them as protons. And at the Cavendish Laboratory in England, Patrick Blackett and Giuseppe Occhialini had caught the positron too in that same year, but they held back publication to gather more evidence, so Anderson published first. The particle had been knocking on several doors. Anderson was the one who opened his and understood what he saw. Step back and take in what had happened, because it's one of the true landmarks of science. A piece of mathematics forced into being by the demand that the electron obey both relativity and the quantum rules had a strange shape at its heart, the spinor, the two-turn object. That shape produced solutions its own author found embarrassing. Rather than delete them, he trusted them, and they predicted a new form of matter. 4 years later, that matter turned up in a cloud chamber, right on cue. The Spinor mathematics was not a formal game played for its own sake. It was describing something real about the universe, so real that it could point to a particle no one had ever seen and be proven right. Dirac shared the Nobel Prize in Physics in 1933 with Erwin Schrödinger, becoming one of the youngest theoretical physicists ever to receive it at 31. And antimatter, once a shocking prediction, is utterly ordinary today. Positrons stream out of certain radioactive atoms all the time, a common form of potassium, the kind sitting in every banana and every human body, throws off positrons as it decays. An average person's body makes several thousand of them a day, each one meeting an ordinary electron within moments and annihilating in a tiny burst of light, completely unnoticed. Hospitals use this on purpose. The scan called positron emission tomography, the PET scan, works by putting a mild positron-emitting substance into the body and watching for the flashes of light where the positrons meet electrons. When a doctor reads a PET scan, they are reading Dirac's antimatter made in the tissue and dying against ordinary electrons mapped out to find disease. A wild theoretical leap from 1931 is now medical equipment in a basement. So the spinner turned out to be describing the real world, sharply enough to predict a new particle before anyone found it. That would be a fine place to stop. But it's the middle of the story, not the end, because the deepest thing spinners do isn't predicting exotic particles in cosmic rays. It's much closer to home. The same two-turn behavior, the same sign flip under one rotation, is quietly responsible for the fact that matter is solid, that a chair holds weight, that atoms take up room and don't collapse into nothing. To see why, the story has to return to Wolfgang Pauli and the rule he'd been guarding all along. Pauli has been in this story from the start, first doubting the spinning electron, then naming its two-valued spin, then writing down the little blocks that compute it. He was one of the sharpest minds of the whole quantum era. He was born in Vienna in 1900, and his godfather was the physicist and philosopher Ernst Mach. He was a prodigy of the loud, undeniable kind. 2 months after finishing high school, he published his first scientific paper. Still a very young man, he wrote a long review article on Einstein's theory of relativity, over 200 pages of it, and Einstein himself praised it, and it stayed a standard reference for decades. He earned his doctorate under Arnold Sommerfeld and went on to help build quantum mechanics itself. The rule that carries his name is the Pauli exclusion principle, and it's one of the most important sentences in all of science. In the mid-1920s, staring at the patterns in how atoms absorb and give off light, Pauli figured out that no two electrons in an atom can be in exactly the same state at the same time. Each electron in an atom is labeled by a handful of quantum numbers, including that two-valued spin, and Pauli's rule says no two of them can carry the identical full set of labels. Every electron must differ from every other in at least one way. They cannot pile up together in one state. They are forced to take turns. That single rule is why the world has chemistry. If electrons could all crowd into the lowest energy level of an atom, every atom would look nearly the same, and there'd be almost no variety to build anything from. Instead, because no two electrons may share a state, they stack up in shells, filling the low levels and then being forced outward into higher ones. The shape of those shells is the shape of the periodic table. The reason one element is a shiny metal and the next is a choking gas is that their electrons are stacked differently, and they're stacked differently because Pauli's rule forbids them from all falling to the bottom. Atoms have their sizes and their personalities because electrons refuse to share. For this discovery, Pauli won the Nobel Prize in Physics in 1945, nominated by Einstein. Pauli was a character, and the stories are worth a moment. He was known across physics as its conscience, the critic everyone feared, because he'd tear into any sloppy idea without mercy. His most cutting dismissal was reserved for work so muddled it couldn't even be tested or shown to be mistaken. He said such work was worse than being wrong, because it wasn't even wrong. There was a running joke called the Pauli effect, the notion that experimental equipment would mysteriously break the moment Pauli walked into the room, and he seems to have rather enjoyed the reputation. And there's a haunting little coincidence at the end of his life. Pauli had spent years puzzling over a certain pure number in physics, the fine structure constant, which is close to 1 over 137. When he fell ill with cancer and was taken to a hospital room, the room number was 137. He died in that room in 1958. He had one more great prediction in him, and it rhymes with Dirac's. In 1930, studying a kind of radioactive decay that seemed to lose energy it shouldn't, Pauli proposed that a tiny, uncharged, nearly massless particle was slipping away unseen and carrying the missing energy off with it. He announced it in a playful letter that opened by addressing its recipients as "Dear radioactive ladies and gentlemen." He worried he'd predicted a particle that could never be detected. Enrico Fermi later gave it a name, the neutrino, the little neutral one. It took until 1956, 2.5 years before Pauli's death, for anyone to catch a neutrino in an experiment. When the news reached him, Pauli wired back that everything comes to the one who knows how to wait. Both of the great theorists in this story, Dirac and Pauli, made their boldest calls by trusting the mathematics to describe particles no one had yet seen, and both were proven right. But there's a nagging question buried in the exclusion principle, and Pauli felt it more than anyone. Why is the rule true? Pauli had found it by staring at data. It worked, it fit, but nothing in ordinary quantum mechanics explained why electrons should refuse to share a state. Why should two electrons, which have no way of even knowing about each other in the usual picture, be so strict about staying apart? Pauli suspected the answer had to do with spin, with that two-valued property, and with relativity, but pinning it down took him years. And when the answer finally came, it turned out to reach all the way down to the two-turn behavior of spinors, the sign flip at the very bottom of this whole story. The exclusion principle, the rule that gives matter its structure, is spinor behavior in disguise. To see that connection, the story needs to name the family of particles the rule applies to, and then prove the theorem that ties it all together. The particles that obey Pauli's exclusion rule have a name, and Dirac coined it. He called them fermions, after Enrico Fermi, the Italian physicist, who together with Dirac worked out how crowds of these particles behave. A fermion is any particle with half-integer spin, spin 1/2, spin 3/2, and so on. Which means a fermion is a particle described by a spinor, one of those two-turn objects. The word fermion and the word spinor point at the same creatures from two directions. One name comes from how they act in crowds. The other comes from how they act under rotation. They're the same particles. And here's the thing that should stop anyone in their tracks. Every particle of ordinary matter is a fermion. Every single one. The electrons in every atom spin 1/2 fermions. The quarks that clump together to make protons and neutrons spin 1/2 fermions. The whole roster of basic matter particles in the Standard Model, the 6 quarks and the 6 leptons and all their antimatter partners, are fermions, every one of them a spinor. To point at anything and call it stuff, anything with weight, anything a hand can hold, is to point at spinors. The matter of the world is built out of the two-turn objects. The strange thing that needs to go around twice to come home isn't a rare exotic case. It's what everything is made of. There's a second family of particles that plays by opposite rules. and the contrast makes the point sharp. Those are the bosons, the particles with whole number spin, spin 0, spin 1, spin 2. Bosons are described by ordinary vectors and tensors, the well-behaved objects that come home after a single turn, with no sign flip. And bosons are not the stuff of matter, they're the carriers of forces. The photon, the particle of light, is a boson, and it carries the electric and magnetic force. The gluon, a boson, carries the strong force that binds quarks. The heavy W and Z particles carry the weak force. Bosons don't obey the exclusion principle at all. They are perfectly happy to pile into the same state altogether in any numbers at all. That willingness to pile up is what makes a laser work, countless photons marching in the same state, and it's behind the eerie flow of superfluids and the resistance-free current in superconductors. Bosons bunch, fermions refuse to, so the universe splits cleanly into two kinds of things. On one side, matter, made of fermions, made of spinors, particles that take up room and won't share a state. On the other side, forces, carried by bosons, made of vectors, particles that flock together as tightly as they please. Anything anyone would call a thing is a fermion. Anything anyone would call a push or a pull between things is a boson. And the fault line between them is exactly the fault line between the two-turn objects and the one-turn objects, between spinors and vectors, between half-integer spin and whole integer spin. The split even survives when particles clump together. A proton is made of 3 quarks, 3 fermions, and adding up their spins, the total lands on a half, so a proton is itself a fermion, and it obeys the exclusion principle. The rule is simple. Stack an odd number of fermions, and the whole bundle is still a fermion. Stack an even number, and the bundle becomes a boson, coming home after a single turn. A helium atom of the common kind has an even count of these basic pieces, and it behaves as a boson, which is why supercold helium can flow as a frictionless superfluid, all its atoms willing to share one state. Change the count by a single neutron, and the atom becomes a fermion again, and the superfluid trick gets much harder. The whole tower of ordinary matter, atoms and molecules and everything built from them, inherits its fermionness from the odd or even count of spinors deep inside. That common phrase, that matter takes up space, is not a vague slogan. It has a precise cause, and the cause is the exclusion principle acting on all these fermions. Because two electrons can't occupy the same state, the electrons in one object can't be squeezed into the electrons in another without forcing them into states already taken, which nature forbids. Push two solid things together, and their electrons resist being crowded. No ordinary force of repulsion is doing the work. The exclusion rule simply won't let them share. That resistance is why a floor holds up a foot, why a hand doesn't sink through a table, why matter is solid at all. It all rides on the exclusion principle, and the exclusion principle rides on the fact that electrons are fermions, are spinors, are two-turn objects, which brings the story to its last and deepest question. Why does being a spinor force a particle to obey the exclusion principle in the first place? The answer is a theorem, and it's the strongest idea in the whole subject. The theorem has a name that sounds far too dry for how deep it reaches: the spin statistics theorem. What it settles is the link between two things that look, at first, like they have nothing to do with each other. One is spin, the private two-turn or one-turn character of a single particle. The other is how a whole crowd of identical particles behaves when two of them trade places. The theorem says those two things are welded together, and it says exactly how. Here is the setup. Take two particles of the same kind, two electrons, truly identical, the way every electron is identical to every other. In the quantum world, identical means something absolute. There's no hidden label on one that could ever tell it apart from the other. So swapping the two, moving the first to where the second sat and the second to where the first sat, cannot change one single thing a measurement could catch. The world has to look exactly the same after the swap as before. That much is forced by the plain fact that the two are interchangeable. The full quantum description of the pair, though, the wave that carries all the odds, gets a sliver more freedom than the measurements do. When the two particles swap, that description is allowed to do one of exactly two things. It can stay precisely as it was, or it can flip its sign, turn into its own negative, every plus quietly becoming a minus. Both of those leave the measurable world untouched, because what a measurement sees depends only on the size of the wave, and the wave and its negative have the very same size. So nature is handed two options at this fork, and it turns out both get used by two different families of particles. For the whole number spin particles, the swap leaves the description unchanged. Swap two photons, and the wave is exactly what it was. These are the bosons, and their sign never flips. For the half number spin particles, the spinors, the swap flips the sign. Swap two electrons, and the whole description turns into its own negative. These are the fermions, and that one small minus sign turns out to run the world because it forbids something enormous. Ask what has to happen if two identical fermions try to settle into the very same state, the same place, the same spin, the same everything. On one hand, swapping them can't change a thing, since they're already in identical conditions, so the description must come back to itself untouched. On the other hand, the fermion rule insists that swapping them flips the sign, so the description has to equal its own negative, and the only thing that equals its own negative is nothing at all. The description collapses to nothing. The odds of it drop to nothing. It simply cannot occur. Two identical fermions are flatly barred from ever sharing a state. That barring is the Pauli exclusion principle, and here it stops being a separate law dropped in from nowhere. It falls straight out of the minus sign. The exclusion principle is that sign flip put to work. So this is the joint the whole story has been reaching for. The two-turn character of a single electron, the minus sign it picks up when the world turns it once around, is the same minus sign that two electrons show when they trade places. And that second minus sign is exactly what stops them from ever piling into one state. Spin and solidity are one fact, caught from two angles. Now for the honest part, because proving all this properly is far harder than saying it, and the reason is true runs down into the deepest floor of physics. The proof leans on two ingredients working together. The first is relativity, the rule that the laws of physics look the same to everyone, no matter how they move, the very symmetry the Lorentz group carries. The second is a plain statement of cause and effect, that two events too far apart for even light to reach between them cannot disturb one another. Feed those two facts into the quantum description of fields, and the sign is pinned down with no freedom left. Whole number spin has to keep its sign under a swap. Half number spin has to flip it. Neither one gets to choose. The tie between a particle spin and its crowd behavior isn't a quirk of our world. It's demanded by relativity and cause and effect standing together. The first real proof arrived in 1939 from Marcus Fierz, a young physicist working under Wolfgang Pauli. Pauli himself tidied it up and made it general the next year, which is why the whole result often carries his name. One more thing the discoverer of the exclusion principle ended up owning. Over the decades that followed, others built deeper and tighter proofs, some of them routed through a strange move where time is treated for a while as if it were just another direction of space. The theorem has stood through all of it as one of the most solid results in physics. And yet, for all that iron certainty, something odd sits right at the center of it. No one has ever found a simple reason for it. Richard Feynman, teaching the subject to students, stopped and admitted plainly that he couldn't give an easy, elementary explanation for why half-turn spin means the sign flips and whole-turn spin means it doesn't. He said that probably meant nobody had truly reached the bottom of it yet. The theorem is proven cold. Its results run through every solid object there is, and the sharpest minds in physics have still had to hold it a little on trust, certain that it's true, unable to lay out in one plain sentence exactly why. There is one picture, though, that comes closer than any other to making it feel like it could not be otherwise, and it ties the whole subject into a single knot. Draw the swap of two identical particles out on a chart of space and time, the two paths crossing over as the particles trade places. Now set beside it a completely different process, one lone particle sitting in place and being turned a full circle once around. It turns out those two drawings, the swap of a pair and the single full turn of one, are the same shape in the deep sense that either can be bent smoothly into the other with no cutting. They're one loop wearing two disguises. There's an old demonstration with a ribbon that shows it in the hand. Give one end of a ribbon a full twist, and then walk the two ends together, and the twist unwinds itself into a plain loop, the same loop that stands for two particles swapping. So the full turn and the swap really are, underneath, a single move. And that's the punchline of the whole subject. The place every thread pulls tight. A single full turn, worked on a spinner, brings a minus sign. That was the strange fact from the very start. The electron that needs two turns to come home, the plate on the palm, the belt that won't shake loose. And if a single full turn is secretly the same move as swapping two particles, then swapping two spinners has to bring that same minus sign, which flips their shared description, which bars them from sharing a state, which is the exclusion principle, which is why matter takes up room. The minus sign that makes one electron need two turns is the minus sign that makes two electrons refuse to touch. And those aren't two facts sitting near each other. They're one fact followed all the way down. The clearest place to watch the theorem actually working is in two close cousins that behave in wildly different ways for this one reason. Ordinary helium, the gas in a party balloon, comes in two forms. The common one carries two neutrons in its core, and the rare one carries a single neutron. Count up all the little spinning pieces inside each atom, the protons and neutrons and electrons, and the common helium comes out with an even count, which by the stacking rule makes the whole atom a boson, a one-turn object. The rare helium comes out with an odd count, which makes the whole atom a fermion, a two-turn object. That single difference, one neutron, ought to be a tiny thing. It changes everything about how the two behave when they get cold. Chill the common boson helium down to a few degrees above the coldest temperature there is, and it does something no ordinary liquid does. It turns into a superfluid, a liquid with no thickness at all, no friction, that crawls up the walls of its container and flows through cracks too fine for any normal liquid to pass. It can do this because bosons love to share a state. and near that temperature, a huge crowd of the atoms drops into one and the same lowest state and moves as a single thing. The rare fermion helium, chilled the very same way, does no such thing. It stays an ordinary liquid because its atoms are fermions and flatly refuse to share that common state. Only when it's pushed vastly colder, down to thousandths of a degree above the bottom, does it finally turn superfluid too, and it has to cheat to do it. The fermion atoms pair up, two by two, and a pair of fermions is an even count, which makes the pair a boson, and the pairs can then share a state the way bosons do. It's the same trick that lets electrons carry current with no resistance in a superconductor. Two different heliums, one law telling them apart, and the whole gap between them traces back to whether the atoms turn once or twice to come home. People have gone looking very hard for any crack in the rule at all. If the exclusion principle failed even a tiny bit, electrons could now and then slip into states that are supposed to be full, and atoms would give off faint flashes of light, of colors that the rule forbids. Careful experiments have hunted for exactly those forbidden flashes in helium and elsewhere, and come up empty down to fantastically small limits, a few parts in millions and beyond. As far as anyone has ever been able to measure, the rule is perfect. No electron has ever been caught sharing a full state. The minus sign has never once slipped. There is a strange footnote that shows just how special the whole two-way split really is, and it hides in the number of dimensions, the clean choice between plus and minus, boson or fermion, is really a fact about our three-dimensional space. Flatten the world down to a sheet, to just two dimensions, where particles can only slide around on a surface, and the swap argument loosens up. On a flat sheet, there's a way for two particles to circle around each other that has no equal in three dimensions, and it opens a third possibility. A particle that picks up neither a plus nor a full minus on a swap, but a fraction of a turn of sign, something sitting partway between a boson and a fermion. A physicist named Frank Wilczek worked this out and named these in-between things anyons, from the word any, because they can take on just about any statistics they like. They aren't a fantasy. They show up in real, thin, cold, flat systems, in a delicate effect that appears when electrons are squeezed into a two-dimensional layer under a strong magnet. That such things can exist only when a dimension is taken away is the sharpest proof of how deeply the ordinary two-way split is stitched into the three-dimensional world everything actually lives in. There's an even bigger consequence sitting one step out from solidity, and it's the reason there's any variety in the world at all. The exclusion principle is what builds the atom, and with it, the whole of chemistry. Wolfgang Pauli wrote the rule down in 1925, before anyone understood spin, to crack a stubborn puzzle. Why don't all the electrons in a heavy atom simply crowd into the lowest, tightest orbit around the core? Every one of them is pulled hardest there, so by the ordinary logic of settling into the lowest spot, they all should. If they did, every atom would be a tiny, dense ball with all its electrons jammed into the bottom rung, and every element would behave almost exactly like every other. There would be no real chemistry. Pauli's fix was blunt. Each available state holds one electron and no more. Once a state is taken, the next electron is turned away and has to settle for a higher, roomier one. He needed one extra ingredient to make the counting come out right, a hidden two-way property each electron carried, which he couldn't name at the time. That two-way property turned out to be spin, and the deep reason his rule holds turned out to be the spin statistics theorem. The whole thing had been the two-turn objects all along. Follow what the rule then does, and the periodic table falls out of it. The electrons in an atom can't all sit at the bottom, so they stack. The lowest shell fills with the few electrons it can hold, and once it's full, the next electron is forced out into a larger shell, farther from the core, and that one fills, and the next electron is pushed farther still. Layer by layer, the electrons build outward, each new one barred from every state already taken, each finding the lowest empty room left. And the way an atom behaves, how it bonds, whether it's a metal or a gas, whether it's eager to react or utterly inert, is set almost entirely by how many electrons are rattling around in its outermost, unfinished shell. Atoms with a full outer shell are the calm, standoffish, noble gases. Atoms one short of full are ravenous. Atoms with a single loose electron on the outside are the soft, reactive metals. The columns of the periodic table, the families of elements that act alike, are nothing more than a chart of how those outer shells come out, shell after shell, filling in the strict order the exclusion principle demands. So the entire periodic table is a printout of the fermion minus sign. All of chemistry, every reaction, every molecule, the water and the salt, and the long tangled chains that make up living things, comes from electrons being forced to spread across many states because they cannot share. If electrons were bosons, if they were one-turn objects instead of two-turn objects, every last one would sink into the same lowest state. Every atom would collapse into the same dull pattern, and there would be no chemistry, no materials, no biology, nothing to build a world out of. The sheer variety of stuff, the fact that there are many kinds of atoms and countless ways to combine them, exists because electrons are spinors and spinors refuse to crowd. The richness of the whole material world is the two-turn habit spread across 100 and more elements. And the electron's spin leaves one more mark that anyone can feel in a fridge magnet. A spinning charge is a tiny magnet, and the electron's spin makes each electron a minute magnetic needle. In most materials, those needles point every which way and cancel out. But in iron and a few of its neighbors, the exclusion principle and the way the outer electrons interact conspire to line huge numbers of those spins up in the same direction, and all those little needles add together into a force strong enough to hold a note to a refrigerator door. The pull of a magnet is the lined-up spin of countless electrons, the same spin, the same two-turn character, showing itself at a size a hand can feel. The same even and odd counting reaches down inside the core of the atom and sorts the particles there too. The protons and neutrons that fill every nucleus are themselves built from smaller fermions called quarks, 3 quarks apiece. 3 is an odd count, so a proton is a fermion and a neutron is a fermion, and they stack inside the nucleus by the very same exclusion rule the electrons obey out in the shells, which is a large part of why nuclei are built the way they are. There's another breed of particle, though, made of a quark bound to an antiquark, 2 pieces, an even count. Those come out as bosons, and they're among the particles that carry the strong force holding nuclei together, so the fork runs all the way to the bottom. Odd bundles of quarks are the standoffish stuff that makes up matter. Even bundles are the sociable carriers that bind it. The same split, 2 turns against 1 turn, spinor against vector, sorts the world at every level anyone has ever managed to look. The refusal of fermions to share also does something on a scale almost too large to picture. When a heavy star burns through its fuel, and its fire finally goes cold, nothing is left to push back against its own enormous weight, and it begins to fall inward on itself. What can halt that fall, at least for a time, is the exclusion principle. The electrons, and in denser cases the neutrons, get packed so tightly that there are no empty nearby states left for them to move into, and since they cannot share the states already filled, they simply refuse to be pressed any closer. That refusal turns into a pressure, a stiffness with no heat behind it, propping a dead star up against gravity purely because its fermions will not crowd. A white dwarf, a burnt star squeezed down to the size of the Earth, rides on the stubbornness of its electrons. A neutron star, heavier still and no wider than a city, rides on the stubbornness of its neutrons. Only when even that refusal is finally overwhelmed, in the very heaviest cases, does the collapse win outright and the black hole form. The same minus sign that keeps a hand from slipping through a table is, in the end, one of the few things in the whole universe that can stand up to gravity at all. Step back now and look at the whole shape of it, with every piece finally on the table. It began with a crack in something everyone took for simple, plain turning in ordinary space. Spinning a thing around once and spinning it around twice are different in a way that can never be smoothed away. A difference the plate and the belt let a person feel in their own hand. To describe the objects that live inside that crack, the ones that can tell one turn from two, ordinary numbers and ordinary arrows fall short. It takes a new kind of object, one that flips its sign under a single full turn. That object is a spinor. The clean machine for building spinners is the double cover of the rotation group, the group called SU2, a smooth sphere in 4 dimensions wound twice around ordinary rotation. The concrete tools for handling them are the poly blocks, and underneath those, the arrow multiplication of a Clifford algebra, where the sign flipping is just what perpendicular arrows do. Carry all of it up from turning space to turning space-time through the Lorentz group, and it becomes the natural tongue of a relativistic quantum particle. Dirac, hunting for a square root, walked straight into that tongue, and his equation dragged Spinors into the core of physics and paid for it by predicting antimatter, found 4 years later in the sky. And the spin statistics theorem closes the ring, showing that the same two-turn behavior is the reason the world is made of things that keep their distance from each other. One thing stands out in how long the rule ran before anyone knew why it held. Pauli laid down the exclusion principle in 1925 as a working rule, a thing that plainly fit the facts of the atom, and for that single idea he was handed the Nobel Prize about 20 years later. When he wrote it, though, he had no deep reason for it. It was a law that simply worked, pulled straight from the patterns in the data, with a mysterious two-way property standing in for something nobody could yet name. The explanation, the spin statistics theorem, came more than a decade after the rule itself, and Pauli was the one who finally pinned it down. That's the same shape the whole story keeps taking. The strange behavior turns up first, in the plate and the belt, in the colors atoms give off, in the plain stubbornness of matter, and the reason underneath it, the two-turn spinor, gets uncovered only later. Nature had been leaning on spinors for a very long time before anyone knew the word. So it comes back, in the end, to the plate. A plate held flat on an upturned palm, turned one full circle while it's kept level, leaves the arm wound and awkward, and only a second full circle, carried the same way round, lets the arm fall loose again. 2 turns to come home. When a person first tries it, it feels like a scrap of party cleverness, a quirk of shoulders and elbows and nothing more. It's the opposite of nothing. That double turn is the very same double turn an electron makes. It's the plain, visible shadow of the deepest habit of matter there is. The electrons in the hand and the electrons in the plate are two-turn objects, spinors everyone, and because they refuse to share their states, and because they refuse, the plate rests on the palm instead of melting through it. The hand holds together, the plate holds together, the floor holds up the feet, all for that one reason. Everything anyone has ever touched, everything with weight, everything that pushes back when it's pushed, is built out of things that have to turn twice to come home. It's the strangest fact in all of physics, and it is holding the whole world up at this very moment. And a piece of it can still be felt with nothing more than a plate and an outstretched arm, turning and turning once again until the twist finally comes undone.